Welcome back. We now know how to calculate the pH of a buffer. We know how to use the Henderson-Hasselbalch equation to calculate the pH of a buffer. And we also know how a buffer responds to the addition of acid or base into the buffer. Now, what we're going to do in this particular section is we're going to use the Henderson-Hasselbalch equation to shortcut figuring out the pH after the addition of an acid or a base. And the system we're going to do is one of those ones that you did in the last video of finding pH of a buffer solution. We're going to take 0.350 molar hypochlorous acid, HOCl, where Ka is 3.5 times 10 to the minus 8th. And we're going to take 0.115 molar sodium hypochlorite. And we knew that the initial pH of this solution from solving it before was 6.97. And we're going to see what happens when we add some acid to this solution using the Henderson-Hasselbalch equation to calculate our new pH as opposed to doing our BRICE table that we talked about. So always good to identify things. HOCl, that's going to be our acid. NaOCl, we know from our solubility rules that that's going to produce Na plus and OCl minus. And so that is our conjugate base when we're thinking about the Henderson-Hasselbalch equation using the A minus and the HA. This is going to be our HA, and this is going to be our A minus. So what's it going to look like? Well, what we're going to do is we're going to add 0.05 moles of acid, right, just HCl or H plus, to 1.0 liters of this solution. And you might be thinking to yourself, well, why do you all of a sudden jump to moles here when we've been talking about molarity? And remember, all the stoichiometry here happens in moles. And one of the reasons I'm specifically saying moles here is because I don't want to change the volume. Right, if I add 5 milliliters of acid, then I now have 1.05 liters instead of 1 liter, and that changes things, makes it a little bit harder. We're going to do stuff like that, don't worry, but let's keep it easy for now. So we're going to do some of this stuff in moles. So what we are going to do, even though we're not going to do our full BRICE table, I still encourage us to do our BRI table to figure things out. We've got HOCl, we're making H plus and OCl minus, and we start off with 0.350 moles. Right, how did I get from molarity to moles? Right, 0.350 times 1 liter. Volume times molarity is moles. That gives me 0.350 moles. 0.05 moles, that's just what I gave you in the problem statement, and 0.115 moles. Always good to write those units, at least in the first step, even if you don't write them in the subsequent steps, just to remind yourself what units you're using. So what do? Well, this is our B, and then it's R and I before react, and then our initial for our equilibrium problem. We know that anytime there's a strong reaction, that strong reaction is going to happen. Since I have a bunch of H plus sitting around, it's going to react with that OCl minus. It's going to make me some HOCl, and so I'm going to use up as much of this as I can. I'm limited here by my H plus, not by my OCl. If I was limited by my hypochlorite ion, then I'd run out of hypochlorite ion, and I'd still have excess H plus. And then here, this is going to be plus 0.05 moles. And so we have 0.400 moles. I should put some more sig figs here. There we go. 0.400 moles. I got none of this left, and I've got 0.065 moles of this left. Now, what we did before is we just did the ICE part here. We did the equilibrium stuff, but let's go ahead and use the Henderson-Hasselbalch equation. pH equals pKa plus the log of A minus over HA. Now, these are in concentration units, right? But remember, you can't take the log of something with units. So the reason it works is because we have molarity over molarity, and those units cancel. So the question becomes, do I have to convert my I's back into molarity? Okay, well, how would I do that? I divide by my total volume, which is 1 liter. So I'd put my A minus. Which one's my A minus? This one or this one? A minus. Yeah, it's the hypochlorite ion. So I'd say 0.065 moles, and I'd divide by 1 liter, and then I'd divide by 0.400 moles and divide by 1 liter. And what do you notice? Those 1 liters cancel. So it turns out one really cool thing about using the Henderson-Hasselbalch equation is that you don't have to worry about units as much as you normally do because they cancel. So we can use molarity in the Henderson-Hasselbalch equation, we can use moles in the Henderson-Hasselbalch equation, and either works just fine because the total volume cancels in either case. So our pH is just going to be our pKa, which we calculated before, is 7.456 plus the log of that ratio of my A minus over my HA. You plug that into your calculator, and you should get a 6.67 pH. Okay, that's a fairly stark change from our initial of 6.97. I thought we said that these buffers resisted changes to pH, and they do. But it turns out we added quite a lot of acid. We used up roughly half of our A minus of our conjugate base there. And so we're starting to actually limit ourselves because we don't have very much of that left, which means we don't have a very strong buffer left. So we can get relatively large changes in pH when we are starting to use up a buffer, and that's something we'll explore in just a little while. Okay. But the cool thing we learned in this thing is when you're using the Henderson-Hasselbalch equation, you can either use moles or you can use molarity, and that's going to be really useful going forward. What about if somebody asked us to make a buffer? How would we go about making a buffer in the lab? So what we're going to do is we're going to say, what mass of sodium cyanide would be needed to prepare a buffer of pH equals 8.70, starting with 500 milliliters of 0.350 molar HCN. Okay, so we want to make a buffer that contains, oh, there we go. Isn't it nice when Windows tells you what's going on? Let's remind me later. All right, because I'm not in the middle of anything, you know, like making a video or anything. Don't worry. So what are we going to do? Well, the first thing we need to do is figure out what's going to be happening. So we've got this solution. It's got some HCN in it, right? And then what are we going to do? Well, we're going to add the sodium cyanide, which we know from our solubility rules is Na plus Cn minus. So we're going to add some Cn minus. We're going to also add some Na plus, but we don't really care about that, right? It's kind of like writing those net ionic equations. We're just going to write the things we care about. And so we're going to make this buffer in here so that those concentration ratios give us a pH of 8.70. So the first thing you need to do is go ahead and look up the Ka values for that. And I encourage you to do this because I'm going to have you do this on tests and quizzes where I'm not going to give you Ka values. You're going to have to look those up in a table. So go ahead and find a table and see if you can look up the Ka value for hydrocyanic acid, HCN. What I get is that the Ka is 6.2 times 10 to the minus 10th. Okay. So if we're using our Henderson-Hasselbalch equation, pH equals pKa plus the log of A minus over HA. And you'll see some people write it there without the square brackets because it is actually general. It works with moles and molarity. But I'm going to go ahead and write the square brackets there. My pKa in this case is 9.31 plus the log of A minus. How much A minus do I have? Oh, wait, I don't know. So this is going to be A minus. And then how much HA do I have? Well, I've got 0.350 molar, right? Now, you could convert that one into moles in this step, and then you'd calculate moles of A minus, and that's fine. Or what I'm going to do is I'm going to calculate molarity of A minus, and then use that to calculate moles of A minus. There's two different ways to solve this. I know my pH, it's 8.70. Okay? And so I can go ahead and solve this one as minus 0.61 is equal to the log of A minus. Let me keep those square brackets to remind myself this is a concentration. Over 0.350 molar. My way to undo my logs is to take a power of 10 of both sides. So I've got 10 to the minus 0.61 is equal to the concentration of A minus over 0.350 molar. 10 to the minus 0.61, if you type that into your calculator, gives you a number that I didn't put down. Don't you love it when you make good notes? 10 to the minus 0.61, that's going to be 0.2455. And so I get that my A minus concentration, just by multiplying both sides by 0.350, is 0.0859 molar. Now, what I wanted to know is what mass of sodium cyanide to put in. So this tells me the molarity that I need. But in order to get mass, I need moles. And so I'm going to take my 0.0859 molar times 0.500 liters. Right? 500 milliliters is 0.5 liters. And so I get 0.0430 moles of A minus. Right? In this case, it's going to be CN minus. The stoichiometry is that 1 CN minus comes from 1 HCN, or sort of 1 NaCN, and so I have 0.0430 moles of NaCN. And then we're going to multiply by the molar mass, which is 49.01 grams per mole, to find out that we need 2.11 grams of NaCN. Now, what do we do about our significant figures? They get a little complicated in here, right? I've got all sorts of numbers in here. But you know, the simplest thing to do is just look back. What are our least number of sig figs? Here, it's 2. And it's a pretty safe bet to say that means at the end we're probably going to only get 2. And so we say 2.1 grams of sodium cyanide. All right, that's how we can figure out how to prepare a buffer, by adding a salt, by adding a solid to it. Because the nice thing about the solid is it doesn't change the volume. A little trickier, and you'll get a chance to do this in lab, is what happens if you're adding another solution and the volume changes. Here's a hint. When volume changes, do things in moles. When volume changes, do things in moles, because moles don't change when volumes change. Right? That was one of the labs we did at the beginning of the semester. All right. Wrong button. Last one in this section is bases as buffers. We've pretty much focused on acids as buffers so far. We said, how will we make a buffer with a weak acid in its conjugate? But it turns out you can make a buffer with a weak base in its conjugate acid just as well. So what's a weak base? NH3. And our conjugate acid is NH4+. So we can make a weak base and a conjugate acid one. Let's go ahead and do that. We're going to take a solution that was 0.40 molar NH4Cl, ammonium chloride, and 0.30 molar ammonia, and we're going to go ahead and find the pH of that. Now, if you're like, hey, Henderson-Hasselbalch equation, pH equals pKa plus the log of A minus over HA. I don't have anything that's minus charged here. What am I going to do if I have nothing that's minus charged? Because I need a minus charge in order to use the thing that says minus? No, remember, that's a generic. It just says HA is my acid. A minus is its conjugate base. And you're like, well, I'm not talking about an acid and its conjugate base. I'm talking about a base and its conjugate acid. But if we're writing this equation, NH3 plus H2O goes to NH4 plus OH minus, that's our kind of weak base equation, right? Then couldn't we also do this equation, NH4 plus OH minus goes to NH3 plus H2O? Right? It's the same thing, right? We know that those K expressions are just 1 over each other because we reverse the reaction. And here we've got a weak base and its conjugate acid. But here, since we wrote NH4 on the left, we now have a weak acid and its conjugate base. Oh, that's interesting. So it turns out we could do the ICE table, and you can actually even derive a Henderson-Hasselbalch type equation. You can look it up on the internet. I don't encourage you to, and I don't want you to, but you can look it up on the internet and find a Henderson-Hasselbalch type equation to use when you have a weak base and its conjugate. But it turns out that the weak base and its conjugate is also a weak acid and its conjugate when you just reverse the reaction. So this one, you'd be looking up a Kb value, but this one, if I rewrite it slightly just to say that it's falling apart, what do I have? Here I've got a Ka. And if you remember, Kb and Ka are related, that Ka times Kb is equal to Kw. Because it turns out when you try to look up something for this one, you're only going to find a Kb. You're only going to find a Kb for the ammonia turning into ammonium. You're never going to find in a table the Ka of ammonium. Just never going to find it. So we know that the Kb, in this case, we can look it up, is 1.8 times 10 to the minus 5th. Kw is 1 times 10 to the minus 14th. And that's going to be times Ka. We can solve for Ka and find that it is 5.6 times 10 to the minus 10th. And that the pKa is going to be 9.252. And so if we use the Henderson-Hasselbalch equation in this one, we can just say pH equals pKa plus the log A minus, right? We've got nothing with minus, but right, minus is the one that's already lost its proton. So which is the one that's lost its proton? Is it NH4 plus or is it NH3? In this case, it's going to be NH3. It's the one that's already lost its proton. HA is going to be the one that has the proton, right? Those are just generic things. They don't actually have to have the same charge. Okay? So generic, loss of proton is the A minus, has the proton is the HA. And we know those values. That was part of our problem statement. Log of 0.30 molar over 0.40 molar, 9.252. Plug that into your calculator, and you should get a 9.13 as our pH of this buffer solution of a weak base and its conjugate acid, or vice versa, a conjugate acid and its, a weak acid and its conjugate base. So most people will use this shortcut of just converting your base into an acid, but you can do the whole ice table if you really want to. If you forget and you can't think of it, I'm never going to require you to use the Henderson-Hasselbalch equation. You can always do it the hard way, but the Henderson-Hasselbalch equation is usually the easier way. All right, thanks so much. Have a wonderful day.